我们富益科技的 CTO. Now, please join me in welcoming our next speaker to the stage, the Chief Technology Officer of Fuyi Power Tech, Mr. Domenico Valverde. 是不是邀请大家用热情掌声欢迎？Big round of applause. 让我们掌声欢迎讲师。
Thank you. Good evening to everybody. Unfortunately, my Chinese after 2 years I live in Taiwan is not good enough to present in Chinese. So my presentation will be done in English. I hope everybody will understand that. So, in 3 years ago I started here in Taiwan and I started with the Fuyi Power Tech. And we started to develop the first silicon carbide power MOSFET in the company. So first of all, I want to introduce a little bit myself. That is my career. My name is Domenico Valverde. I have been, in the semiconductor field, especially for power MOSFET, since 1983. In November I started in STMicro. Look like yesterday, but 43 years out from us. So, here what we're discussing today is what we have done in Fuyi, and this is the major need that are required for the marketing is for high efficiency system for solar, for electrical vehicle, for solar inverter, for central power supply, for industrial drivers. The major challenges that we found today on this on the silicon carbide MOSFET is the conduction losses and the high switch losses and the gate or stress for the sleep conditions. The marketing in the meantime is requiring cost-effective, high performances, and scalable platforms. So next generation silicon next generation silicon MOSFET platform is designed for high efficiencies, high voltages, and high reliability. And our device mostly are based on DMOS. It's a very old architecture. Then I developed in this architecture the first silicon carbide MOSFET for STMicro Electronics in 1984. So this represents the status of the art for conduction and switching. And the roadmap I developed in the last 3 years together with my team, HPD, that is splendid engineers, and is including the G1, was the first generation, the G2, and the G3, that is the current one that we are calling G3 Supergate, because the gate is very excellent and very robust. And the G4 is the one that currently we are working on, is the Super Junction. It's very similar to the Super Junction in silicon carbide, in silicon resistance now. But the technique is how we pick up the P minus P wave. Now the P wave is totally different from the one we found with the market. So now this is on the picture here is 1,200 volt in silicon carbide, the MOSFET G3 Supergate, we call Supergate 15 million RDSO. It's pretty small, and on the left hand side we can see that the first generation we have developed in 2022. It was 4.8 million per centimeter square. Generation 2 we made the upgrade in 2023 and it was 4.2 million centimeters square. And now we got the G3 that is the top one in our we already can measure directly on with 2.5 million centimeters square. On the next generation, the Sant'Agata, we are planning to improve the same, say, improvement we have done for between G2 and G3, and continuing improving the around resistivity and make the RST more smaller, and actually the conductivity and the wooden density for centimeter square, and the increase because one of the major core requests from our customer currently is the breakdown their voltages and reducing the meantime the production cost because we are trying to reduce up the distributed masses. So this is in short what is what has been done travel between Q3 2022 and Q2 2025. And as been, this is I want to repeat what has been what I talked about the previous slide. The G1 is 4.8 million centimeters square. The G2 is 4.2 million centimeters square, and the Supergate now, the generation 3, is showing 2.5 million centimeters square. What has been done between generation 1 and generation 2? It is not just merely reduce increase the quantity of the channel, on the surface, the channel length, but it's also one optimization of the channel distance, the JFET resistance, and mostly there are one improvement on the metallization of the lead on the source, where the resistivity, the resistance we got between the silicide and the top metal, it has been at least reduced half. So based on that, the specific resistance on we bring from 4.8 to 2.5. The current density now we have is between 3.7 ampere per millimeter square to 4.5 ampere per millimeter square. And the beautiful things that we has been able to reach is supporting the breakdown voltage from the gate from 31 volt to 37 volt. I mean, respecting all the remaining parameters and based on the gate oxide thickness mostly, we reach 37 volt before the gate breakdown. So this means that all the ability tests can be done honestly at 30 volt, and we will have no issue to passing HTGP in these conditions here. So after this is the last technology we have in G3 Supergate. We call Supergate obviously because for us switch from 31 volt to 37 volt without breaking the gate oxide has been a success, and the appropriate name that we choose for this technology is just Supergate. And based on the generation 3, we also, in the meantime, optimize the VGS driver. The VGS driver, we have two different versions. Is to notify that it's the same chip. And for 15 volt, we have the 6 million. And with the same voltages, we can get 5 million. No, it's about with 18 volt, we can get 5 million. So the device list, the die list, we can see on the left of 18 volt, and the device list for the die list for the 15 volt, we can see on the right side. This platform at the moment is already 1,200 volt, and in middle September we will have available the 650 volt as well with the same characteristic in G3. And at the end of October, we will have the 3,300 volt in G3 also. So this is what gravity G3 software. And now in this slide here, there are different comparison because under our calculation and simulation, we simulated the supergiant, the G4, and we drop our DSO from centimeters square from 2.5 million to 1.7 million. So also, you can see just here that the Supergate 1200 volt is already available, also same engineering, same available. And generation 4, the Super Johnson, where we are working, the first lot, will be planned in Q3 2026, and will be the 650 volt. And we'll have 1.1 million RSP, specific resistance on. So then the plan is develop all, range of voltages from 650 to 1,400 volt, and 1,700 volt, 3,300 volt, and we are in program, but still has been not decided. There are no, economic plan behind. Our plan is also put in development 4,500 and 6,600 volt. But this, still should be supported by the economic, calculation, if it's convenient to do, if the second end of the market is allowed to do this kind. So, this is just in conclusion. And what we are currently allowing in G3 is high switching efficiency, low specific resistance, because we think we are one of the first on the world that is have a technology 2.5. Someone is claiming to someone is claiming to have 2.1, but when I hear this kind of thing on demos, where the calculation based on the substrate resistance and egg resistance is coming up more than 1.2, and I'm thinking it's quite strange. So this is, I'm thinking, when we got 2.5 probably is one near to the theoretical limit or the affordability for the demos. Next, for sure, should be the Super Johnson, or maybe the Super Johnson with the trenches. So at the last, the generation 3 is also available with we are calling BTS, a very thick top metal. The very thick top metal will allow to have a very good resistance to the short circuit. So for this one year, I believe that for generation 3 is a milestone right now in 2025, where we can trust that the next should be only the Super Johnson. Thank you very much. That's it.